all about polynomials. And we have actually talked about some polynomials already when we talked about parabolas, when we talked about like x to the third. So we've looked at some of this stuff before, but we are going to be extending it into some more polynomials. So first of all, we just need to kind of go through some definitions. Not like I'm going to give you a test and ask you to write these definitions or anything like that. It's just so that when I ask you, can you tell me the degree in this problem, you know what I'm asking for, okay? So in general, a polynomial is really just when you have terms added and subtracted. In a polynomial, there are no negative or fraction exponents. So all of our exponents have to be nice. 0, 1, 2, 3, 4. Nothing crazy. So you guys don't like fractions? Well, we won't have those in polynomials. If you don't like radicals, we don't have those in polynomials. So a polynomial is something like, for instance, 5x to the 6th plus 3x cubed minus 2x minus 4. That's an example of a polynomial. When I ask for the degree in a polynomial, that is the highest power. So if all these terms are added and subtracted, we can just look at it. It doesn't have to necessarily be the first one, so you should look at all of them. But if I'm looking at this example polynomial, what would be my degree? 6. That's the highest exponent in that thing. Okay, if I ask you for the coefficients, what are those?
Numbers.
Excuse me. So the coefficients are just your numbers being multiplied with your variables. So like the 5, the 3, the negative 2. Those numbers out in front of your x. Those are the coefficients. What's a constant? So it would be a number without a variable.
Dang. I wish I would wipe it off today so I could go with it.
Thought I made you angry already. So what's the constant in this example? Negative 4. Yeah, since it's a minus in front of it, we'll go ahead and call it a negative 4. The leading coefficient.
I remember this, but I don't.
You know you've seen the terms before, but...
Is it the one that, so wouldn't it be like 5 because it's the one with the highest power?
Yes. So it's just the coefficient of the term with highest power.
Anyone else just had my stomach?
Did you eat lunch?
Yeah, I ate Subway.
So the leading coefficient here is the 5. Again, not to be confused, it doesn't have to be the first coefficient. You just have to find that variable with the highest power, and it's the coefficient of that term. And the leading term is just the term with the highest power. So what would be my leading term here?
5x.
Yep, that whole thing. Out of that, the term, what you're going to hear me talk about the most is the degree. That's going to be the main piece that we keep revisiting. We'll talk about it today, and it will be a common question for the rest of this chapter. We'll always need to look at the degree of our polynomial before we do anything else. When we graph these, if you think about the graph of like x squared or x to the third, the graph is always nice and smooth. You're not going to have any corners in the graph. You're not going to have any breaks in the graph. It's just a nice curve. If I asked about transformations, all the transformation rules are the same as what we've learned before. So there's nothing new there. I'm not going to add any of those. Typically Typically, we're not going to use transformations to graph these, but if we did, it's just the same thing that we've learned in the past. Alright, so what I want to do first is look at some problems and decide if these things are polynomials. And if they are, we have to give the degree. So is A a polynomial? Yes. What is the degree? 4. The highest power is just a 4. B. I told you that if it's a polynomial, your exponents have to be like 0, 1, 2, 3, 4. Being under a radical is like a fraction exponent.
Yeah, so no.
So this is not a polynomial because you have a variable under a radical. So is C a polynomial? The top alone is. If I just looked at the bottom, that would be, but
It's in a fraction.
it's in a fraction. If a variable's on the bottom of a fraction, that's like saying it has a negative exponent. So this one is not, because you have that variable in the denominator. So those are the two main rules that would be broken when I'm asking you if it's a polynomial or not. If you have a variable on the bottom of a fraction or a variable under a radical, it's an automatic no. Alright, D?
I want to say no.
It's kind of a weird one,
Yeah, I don't know.
but does it break any of the rules? Do I have a negative or a fraction exponent? So it is actually a polynomial, but the degree piece is a little tricky. So degree is like saying how many variables are there. 0 doesn't have any variables, but isn't, if I said 0 times x, does that equal 0 still? And that has one variable. If I said 0x squared, does that still equal 0? And that has two variables. And we could play this game for the rest of the day. I could put any x with that I want. So the rule is, and this is only when it's equal to 0, there is no degree. Because you could put any x with that, and it would still be equivalent. Now, E is similar but different. It's still just a function equal to a number, but that number is no longer 0. So is this one a polynomial?
Yes.
Yes, it didn't break any rules. Now the degree. Is 8 the same thing as 8x? No. So how many variables does this have in it? None. So this one has a degree of 0. So the only time you'll say no degree is if it's just something equal to 0. If it's any other number, 2, 3, 8, negative 6, there's no variables there, so it's a degree of 0. Alright, the last one. This is written a little bit differently. All the polynomials I've given you so far have just been added or subtracted. This one is in factored form. It is still a polynomial because we could multiply that out. I could take x minus 1 and square that and then distribute the negative 2x cubed, so we could get it to the other form. When I ask you the degree, degree is the highest power, but that's only if it's written in the standard form, something plus something plus something. If it's written in this factored form, we have to think about, if I multiply this all out, what power of x would I get? Now, I don't really want to multiply everything, because I only care about that term with the highest power, correct? So let's just think about what that would be. We have this negative 2, we have an x cubed. If I take this x minus 1 squared, we have an x squared, so we would end up with an x squared in that. If you multiply these, x to the third times x squared, that's an x to the fifth. So overall, what's my degree there? 5. And we will practice that a lot more. So if you didn't quite get it there, don't worry, we'll look at that some more. How to get the degree if things are in factored form instead of all multiplied out.
I don't know why, but I guess I thought you were supposed to multiply right there.
Well, it's tempting, just say like a 6, but you have to think about if it's.
Isn't it like if it's, yeah, and then parentheses.
There you add.
Like that.
Here you multiply.
Yeah.
Other questions to this point? So here's what I want you to do. Grab a graphing calculator. And I want you to do the next example using your graphing calculator. Just draw me a really rough sketch, so I'm not even really looking for any exact points. I just need a sketch of what each of those 4 things look like. So x to the third, we've seen that one before. What's x to the fifth look like?
Almost like the same, but like skinnier.
Yeah. What about x to the fourth? Looks like a parabola. How about x to the sixth? Just a skinnier parabola. Yeah. Okay. So what we're actually seeing is if we have x to a power, it's always going to look like one of 2 things. It looks like x squared if the power is even. So x squared, x to the fourth, x to the sixth, x to the eighth, they all look the same. Or it looks like x cubed if that power is odd. As that exponent gets bigger, what did you say happened to the shape of the graph?
It like gets skinnier.
Yeah, it gets skinnier, it narrows. And that's the only obvious difference. Same shape, just gets narrower with the higher exponent. So this leads us into what's called the end behavior of the graph. And when we start graphing these polynomials, the first question I'm going to ask every time is what's the degree? And the second question I'm going to ask is what's the end behavior? And we're not going to be real scientific about this. When I'm talking about end behavior, I just want to know what direction are your ends going? Are they both pointing up? One down, one up? So you're just drawing me a couple arrows. That's all you're doing when I ask for that. And so as it turns out, end behavior is completely determined by the leading term. So if I'm looking at a polynomial, I just have to find the term with the highest power of x, and that will tell me which direction the ends are going. If that term has an even degree, then what do we know about those ends? Think about x squared, x to the fourth, x to the sixth. What's going on with those? They're both going up. So as long as we have a positive coefficient, they're both up. What if I said negative x squared? What would happen?
They both go down.
Yeah. So the ends go the same way. As long as it's a positive, it's a regular upward parabola. But as soon as I throw a negative coefficient, it just flips them both down. So if that leading coefficient were negative, my end behavior would be down, down. Alright. If we have odd degree, so if we have a positive x cubed, what are my ends doing?
1 up and 1, or how do you want it? 'Cause this
Well,
side would go down and this side would go up.
Yeah, we'll go left to right. So the left side is pointing down, the right side is pointing up. But if I made it a negative x cubed, what does that negative do to our graph? Flips it, so it became up and then down. So we will just look at the leading term and decide the end behavior from there. So we'll do a few together and then we'll give you guys a chance to try it. So in this polynomial, what do I look at?
The leading term.
Mm-hmm. So my highest power of x is 3, so we just look at this 4x cubed. So we know if it's an odd power, looks like a chair, the ends are going opposite directions. It's a positive coefficient, so it doesn't flip. So my end behavior is down that. Now, if you get confused, how can you check? Yeah, couldn't you use your graphing calculator and graph that picture and see which way the ends are going? Absolutely. Easy way to check yourself. I'm not taking away the calculator. You have that option. But all we have to look at is that first term. So in this one, my leading term, my highest power of x is right here. So my leading term is negative x to the 6th. Right. Even power means the ends are going the same direction, but a negative is going to take that and flip it upside down. This one. When we decide our leading term, it has to be in a polynomial that's all multiplied out. So in this, we have to think about if we multiply this whole thing out. So we have that 3 in front. All we care about is the highest power of x, so that's just an x. This one, we would get an x squared. So if you multiply those together, what do we get? So x cubed, what's our end behavior? Like a cube. We have a positive coefficient, so it doesn't flip. If we multiply it all out, we have 1/2. In this parenthesis, my highest power is an x squared. In this one, we have an x squared cubed. What do we do with those exponents? Multiply. Yeah, because it's like a power to a power. So that one would become x to the 6th. This would just. So altogether we get 1/2 x to the 2 plus 6 plus 4 plus 12. So what's my end behavior? 12 is even. Evens go yeah. Go the same direction. It's positive 1/2, so go up, up. Okay, here's what I want you to do. The next 4 are matched. So you can use your calculator to check yourself, but I'd like you to try it without first. So like look at this equation, figure out what the end behavior should be, figure out which graph has that end behavior. So try to match them without your calculator, but you can then use your calculator to double check yourself if you would like. so what should our end behavior be? Up, up, so that's C. Okay, H, 3x cubed. So x cubed should be down, up, so that's graph B. Alright, G, negative x to the 6. So even powers look like a parabola, but a negative flips it upside down. So it should be down, down, so that's graph A. And K, negative 7x to the 7. So odd power looks like a cube, but the negative flips it, so it's up, down. We do okay on those? So what I'd like to do, I want to get through some terms. We're going to talk about maximums and minimums, and then we're not going to be able to finish this whole handout today, but we'll get close. Alright, when I talk about turning points on the graph, that's when the graph changes direction. So in other words, if I'm looking at a graph and it's increasing, then it switches and starts going down, it switches and starts going back up. These points right here are the turning points. It's where you switch from going up to going back down, or vice versa. So you can have multiple turning points on one graph. When I ask you for the extrema, that's just another word for maximums and minimums. And we have two different types, absolute and local. An absolute maximum or minimum is the highest or lowest on the entire graph. Okay, so you look at the whole graph and you can find a point where nothing else goes above that, or nothing else goes below that. A local, it doesn't have to be the highest or lowest on the entire graph, it's just higher or lower than the surrounding points. So we're going to look at a couple graphs and see if we can tell the difference between these two. Okay, so I have two different graphs. First question, I want the local extreme points of F. So I need the local max and the local min on graph F. So a local max, it doesn't have to be the highest on the entire graph, it's just higher than anything around it. So what would that be? Okay, local min. Not the lowest on the entire graph. It can be, it doesn't have to be, but at least lower than the points around it. So that would be?
I was gonna say EH, but
AB is also, isn't it?
I was gonna say couldn't it be?
Yes, you can have more than one. So EH is definitely lower, but AB is still lower than the points on either side of it, so it's okay. So on G, local max, is there a point on G that is higher than the ones around it? Mm-hmm. Local min, is there a point on G that is lower than the points around it? Now I want the absolute. Do I have a point that is the highest point on the graph where nothing else is above it? They keep going up forever, so there is none. Do I have an absolute min on F, a point that is lower than everything else on the graph? EH. Okay, G, does it have an absolute max, the highest point on the entire graph? No, because that keeps going up forever. Does it have an absolute min, a point that is lower than everything else on the graph? No, so that one didn't have any absolute maxes or mins.
That's not that bad.
Good. Hopefully it's not a horrible first day back. If you don't mind, I just want to talk about the bullets under turning points and then I'm done today. So we can look at this. How many turning points does this graph have? 3. In general, your degree has to be at least one higher than your number of turning points. So if I have 3 turning points, it has to be at least degree 4. If I give you the polynomial, your number of turning points is 1 less than the degree. So if it's degree 6, how many turning points can it have? 5. Alright, that's the last piece I wanted to mention. So here's what we're going to do. I have a handout. You are not doing the whole thing. So
Wait, what you just went over is these 3 bullets?
Yeah.
Yeah, that makes no sense. Yeah, I didn't look at it, because I kind of glanced at it, and I just looked at it.
yeah, I put the definition like in terms of variables there, but I figured it would just make more sense. We talked about it with these, right? So all I want you to do on this is 1 through 12. Tomorrow we will wrap up the last part of the notes and we'll work on the last few questions in class. So 1 through 8, those are in behavior, so you're just drawing me the arrows. 9 through 12 asks you how many turning points. So for instance, number 9, what is the degree of that? 5. So how many turning points can it have? 4. And that's all you have to write down.
But
Just the 4.
do you get the number?